Here you get to take a look at Johann Kepler, a key figure in our understanding of celestial mechanics. Now, you can't say that Kepler by any means lived a charmed life. He was alive during a time in which the bubonic plague, the Black Plague, the Great Plague, made a comeback throughout Europe. His father left him at the age of 5. He was a mercenary who most likely died in war. His mom was an herbalist, and she was accused of witchcraft. Kepler's first 2 children died in infancy, and he had a hard time maintaining employment as a mathematician. Now, he was a gifted mathematician, and he did have one stroke of luck in his life, and I have another video that you can watch in this segment that details the work done by Tycho Brahe. And toward the end of Brahe's career as an astronomer, he hooked up with Kepler, and Kepler was able to inherit, albeit after a long time of difficult work, the work done collecting data on the motion of the planets from Tycho Brahe. And from the data that he gathered on the motion of the planets, he concluded 3 things. So Kepler, in the end, achieved the sort of immortality only afforded to the likes of Galileo and Newton and Cavendish and Michelson and so forth. 3 laws. Kepler determined 3 laws about the motion of planets. Number 1 is called the Law of Elliptical Orbits. Two is called the Law of Equal Areas. And 3 is often referred to as the Law of Harmony. Well, the Law of Elliptical Orbits kind of speaks for itself. What Kepler discovered was no planet orbits around the sun in a perfectly circular orbit. Now, I'll caution you, whatever textbook you read, if it tries to illustrate the notion that a planet orbits around the sun in an elliptical path, it often highly exaggerates that elliptical path, and it's not uncommon to see diagrams of this sort that lead you to believe that a planet is sometimes so much closer to the sun at one point in the year than it is at another point in the year. Truth is, if you could actually see the orbits, if you could get in a spacecraft and fly up above what's called the plane of the ecliptic, let me draw the sun one more time. This time I'll leave out the corona on it. Instead of viewing straight down, there's my very eager mother just served us nachos. Mercury, Venus, Earth. Well, okay, so all the planets are orbiting in what appear to be pretty much circular paths. This can be viewed from another aspect. What if we had the sun here, and then we look at Mercury, Venus, Earth, and so, well, they all orbit very nearly in the same 2-dimensional plane, and that plane is called the plane of the ecliptic. Well, if we define the plane of the Earth's orbit, that's called the plane of the ecliptic, and almost all the other planets share nearly the exact same orbital plane, give or take a deviation of a few degrees, with the exception of one dwarf planet. Pluto orbits at a significant angle relative to the plane of the ecliptic. So, if you could fly up perpendicular above the plane of the ecliptic and look down at any of the planets, and then hit the fast forward button on your cosmic remote control, you'll find that any given planet you view appears to orbit in a path that looks, well, not quite like that. There we go. Yep, that just looks like a circle, centered with the sun. But truth is, it's slightly elliptical, just slightly being the key word. So it's helpful to draw these exaggerated versions of elliptical orbits just so we can relate to the ideas expressed in Kepler's laws. But keep in mind that these elliptical orbits, maybe instead of calling this the law of elliptical orbits, we should call it the law of slightly elliptical orbits. Okay, so there you have it. So this law of equal areas just expresses the idea that the speed at one point and the tangential speed at another point are not equal if the path is not perfectly circular. So there's a distance we can call r1, the distance from the center of the sun to the center of the planet, and then there's a distance r2, also from center to center when the planet's farthest away. Now when the planet's at its nearest approach to the sun, we refer to that location as perihelion, just meaning closest to the sun, and aphelion represents the point farthest from the sun. There's no net external torque acting on a planet as it orbits around the sun. That means that angular momentum has to be conserved. And for angular momentum to be conserved, mass times speed times distance has to be a constant. Well, if mass and speed and distance are all a constant, then that means when r is small at perihelion, then v is larger. So let me exaggerate that as well. Let's draw v1 as a long arrow and keep v2 as a short arrow. So something like this. M times v1 times r1 equals m times v2 times r2. We could cancel out the m. The speed at some second point is equal to the speed at some original point multiplied by a ratio of radii. That corresponds perfectly with this notion. Imagine a line like a tether. Imagine the planet's like a giant game of tetherball. And imagine how many degrees of the ellipse, what fraction of the total area of the elliptical orbit is swept out by that imaginary line in some time interval. Now you can imagine any time interval you want. We can imagine a time interval that moves the planet from perihelion to this point. Maybe that represents about 1 month of motion, something like 1/12 of the orbit, if it's the Earth. Well, now imagine the longer tether, the longer line that separates the sun and the planet when the planet's at aphelion, and try to picture the exact same amount of time. Because the velocity is smaller, it doesn't travel as great of an arc length. The one thing that's the same, it's not the speed, 2 different speeds. It's not the distance, 2 different distances. It's not the arc length, 2 different arc lengths. Do you know the one thing that is the same? The area that's swept out by that imaginary line is an equal number of square meters or square miles or square astronomical units or whatever units you choose to use. The area swept out by an imaginary line connecting any planet to the sun will sweep out equal areas in equal time intervals. That's a long-winded way of saying the law of equal areas. If you want to write that in your notes as you follow along with this video lesson, I'll say it one more time. You can copy down the law of equal areas. It suggests that an imaginary line connecting any planet to the sun sweeps out equal areas in equal intervals of time. Probably better just to express it with a diagram like this. But keep in mind that the law of equal areas is consistent with the law of conservation of angular momentum. However, in the year 1571 to 1631, prior to the Principia being published by Isaac Newton, there was no concept of a quantity known as angular momentum, and certainly no law known as a law of conservation of angular momentum. So Kepler, in a way, was ahead of his time by noting this law about the area swept out by an imaginary line. Now, the law of harmony, we've actually already seen this one. If we set gravitational force equal to centripetal force, then we can say g times the mass of the planet times the mass of the sun divided by the distance between the planet and the sun squared is equal to the mass of the planet times its orbital speed squared divided by the orbital radius. So for a circular orbit, this works out. One of the r's cancels, the m cancels, and v is equal to the square root of gm over r. Now if we make another substitution for a circular orbit, that v is equal to circumference 2 pi r divided by t, then in the end we derive an equation that says the period of orbit for any planet is equal to 2 pi times the square root of its circular radius cubed divided by the product of g and m. What if you compare any two planets? Let's say that's the sun, there's Mercury, there's Venus, and then let's skip Earth, Mars, the asteroid belt, and let's compare the orbit of Venus to the orbit of Jupiter. Which one takes more time? For sure, Jupiter. How much more time? Well, if I knew how far away it was, maybe Jupiter, well, there's a definite value and I don't know it off the top of my head. Let's just speculate and guess that Jupiter orbits about 5 or 6 times as far away from the sun as Venus's orbit. Then does that mean the length of its orbit is about 5 to 6 times as many days or years or months or whatever it takes? Well, no, because it's not a simple 1-to-1 ratio. Period squared is proportional to radius cubed. This gives us a law of harmony. Everything else in this equation is a constant. Period is equal to 2 pi divided by the square root of gm times r to the 3/2 power, or period squared is equal to 4 pi squared over gm times r cubed. So 4 pi squared over gm is equal to period squared over radius cubed. For which planet? For any planet. So if I compare planet 1's orbital period to its orbital radius cubed, I get the exact same ratio as a second planet's period squared divided by its radius cubed. So expressing the law this way is putting it in terms of Kepler's law of harmony. It gives us a way to compare the length of time for any planet's journey around the sun compared to another. We'll get into this in more detail in a future video lesson. For now, I want to give you a broad overview of Kepler's 3 laws: the law of elliptical orbits, the law of equal areas, and the law of harmony.